Hi, this video is brought to you by Professor Jen Chen at California State University, Long Beach. I will be discussing long division and synthetic division for polynomial functions. Dividing polynomials is much like dividing numbers. Let's illustrate the terminologies through division using numbers. I want to divide 38 by 7, and I say the number 38 dividend, and I call the number 7 divisor. Ask ourselves, how many times does 7 go into 38 completely? The answer is 5. Some leftovers. To figure out the leftover, I take 5 times 7, which gives me 35, and take 38 minus the 35. So the 3 is the leftover. We don't just write 3, we write 3 over 7. This is because we think of it 5 times 7 as 35, but then it's dividing by 7, and then add additional 3 over the same divisor, 7, to give us the overall 38 over 7. 5 here is called the quotient. 3 here is called the remainder. Another way to think about this division process is that I can write 38 as 7 times 5 plus 3. Again, 7 will be called the divisor, 5 is the quotient, and 3 is the remainder. The same set of terminologies apply to polynomial divisions. If p of x and d of x are polynomials, with d of x not equal to 0, we need this condition because division by 0 is not allowed. Then I can think of p of x as d of x times q of x plus r of x. Where the d of x is the divisor, q of x is the quotient, and r of x is the remainder polynomial. One consequence of this division is that the degree of the remainder polynomial has to be strictly less than the degree of the divisor polynomial. Or we can also think of the polynomial division as p of x equals q of x plus the remainder polynomial r of x divided by the divisor polynomial d of x. This will be the second way we can think of the polynomial division. The same degree requirement applies to this expression here, and because the degree of the r is less than the degree of d, we are pretty much guaranteed that this rational expression is written in its most reduced form. If the degree of the r of x is actually greater than or equal to the degree of d of x, then one can perform a long division one more time to reduce that degree down by 1. Next, let's consider doing an example of long division and try to express our results in both forms. The question here is basically saying that the first polynomial is the dividend, and the second polynomial x minus 4 is the divisor. So essentially we're looking for an expression to write 6x squared minus 26 plus 12 divided by x minus 4. Although we can write the results in different forms, but really the process of doing long division is the same. Long division goes like the following. First, we put the dividend inside. We have to make sure that it's written in a descending order starting from the highest polynomial degree. In this case, 6x squared. We have to fill in all the missing terms in between the highest degree and the constant term. In this case, all the degrees are present. We've got the degree 2, degree 1, and the degree 0, which is the constant term, all into place. We put the divisor function on the outside. The process of the long division is basically an iterative process, where we keep dividing the leading term in the dividend by the leading term in the divisor. To start, I look at my leading term in a dividend, which is 6x squared. I divide that by the leading term in the divisor, which is x. If you're not yet comfortable doing that division in your head, I would recommend you write it down on the side as a scratch work. 6x squared divided by x gives x. That becomes the leading term of my quotient. Once I figure out what this term has to be, I take this term and distribute it to every single term in my divisor and then put it below the dividend. So I have 6x squared minus 24x. And then subtract the two polynomials to try to get rid of the highest degree that's present here, which is x squared. Clearly, 6x squared minus 6x squared is 0, and that was my purpose, was to get rid of the 6x squared. And then I have negative 26x minus negative 24x. That becomes negative 26x plus 24x, which gives me negative 2x. Next, I need to carry as many terms as needed in order to match up the number of terms in my divisor. In this case, I have 2 terms in my divisor, which means I need to carry one more term down from my dividends. Once the number of terms match up, I do the same process of taking the leading term in my dividend divided by the leading term in the divisor. In this case, it would be negative 2x divided by x, and that gives me negative 2. This is a term that's going to go into my quotient. Now take negative 2 and distribute it into x minus 4. I would then get negative 2x plus 8. Now subtracting those two polynomials successively get rid of the first leading term. I'm left with 12. This means my quotient is 6x minus 2. My remainder r of x is 4. With the divisor being x minus 4, if I want to write it in the form of equation 1 here, I just need to do d times q plus r. And that would give me x minus 4 times x minus 2 plus the remainder 4. Or if I want to write it in the equation 2, which is going to be q of x plus r over d, I would get 6x minus 2 is my quotient plus the remainder 4 divided by the divisor x minus 4. Notice that the degree of the remainder is strictly less than the degree of the divisor. Make sure you actually understood the concept. I encourage you to practice this next example by yourself. You can express your final answer in one of those two forms. As we put the dividend inside the long division process, we make sure that it's listed in a descending order and a no missing terms is there. It turns out that the x cubed term is missing, which means we need a placeholder of 0 as we put it in. Similarly, for the divisor, we need to put a placeholder of 0x, the missing term. If I divide ax to the fourth by 2x squared, I would get 4x squared. I then take that, distribute it in to every single term in the divisor to get ax to the fourth plus 0x cubed plus 4x squared. Subtracting those two polynomials then gives me 2x squared. I have 3 terms in my divisor, which means I need to carry 2 more terms down to match up. I have 2x squared minus 3x plus 1, simply carrying that down. I then take my leading term in the new dividend, divided by the leading term in the divisor, and that is simply just going to be 1. Take the 1, distribute it in, and that's basically just copying every single term from the divisor. And now subtract those two polynomials. The 2x squared is cancelled. I get negative 3x, and no more constant term. If I now write my result in form of the equation 2, I will get ax to the fourth plus 6x squared minus 3x plus 1. That's the dividend divided by the divisor, 2x squared plus 1. Equals to the quotient, which is 4x squared plus 1, plus the remainder, but the remainder is negative 3x, so that becomes negative 3x on top, all divided by the same divisor of 2x squared plus 1. Again, notice that the degree of the remainder is less than the degree of the divisor. Next, we present a quick alternative to perform polynomial division, and that is called the synthetic division. The limitation of the method is that it can only be used when the divisor is of the form x minus a constant c. For example, in example 1 we presented, the divisor was x minus 4, which means c is equal to 4 in that case. What we do in synthetic division is we only carry the coefficients and just ignore the variable x altogether, because really all that matters is what we do to the coefficients. We extract the coefficients from the dividend and then put it inside here. In this case, in the descending order, it would be 6, negative 26, and 12. Put this number c on the left outside. We put a plus sign on the right outside. First step is to carry the 6 down, and simply just don't do anything, just carry the 6 down. Then multiply the divisor 4 with this number 6, and then put it right below the negative 26. So that gives me 24. And we add those two numbers next. So negative 26 plus 24 gives me negative 2. Then take 4 again, multiplied by negative 2, get negative 8, and put it right below the 12. We again add those two numbers to get 4. We'll stop here because there are no more numbers to do. And this last number here is called the remainder, and we typically put a comma right in front of it to tell us that that is the remainder, and everything before it is going to be part of the quotient. The degree of the quotient is at least 1 fewer than the degree of the dividends. And if this first number is not equal to 0, that means the degree of the quotient is exactly 1 degree less than the degree of dividends. In this case, the degree of the dividend is 2. That means the degree of the quotient must be 1. That means the 6 must correspond to the linear term, 6x, and the negative 2 must give us the constant term of negative 2. The remainder will always be a number, in this case 4. Again, this allows us to write the original problem 6x squared minus 26 plus 12 divided by x minus 4 as the quotient 6x minus 2 plus the remainder 4 divided by the divisor x minus 4.